Welcome back, everyone. I make it 10:45. It's a real pleasure to introduce Shinichi Mochizuki, who's going to talk to us about his progress on the formalization of IUT.
Okay, thank you. Can you hear me? Is my audio okay?
Yes, this is all fine. Thank you.
Okay, thank you. So first, I would like to begin by expressing my gratitude to the organizers of this conference. Especially since I am very much a newcomer to the field of formalization. But I have been very deeply impressed by in listening to the other talks, by the numerous interconnections and parallels between my own experiences and the topics discussed by experts in the field. So, so I will be talking about progress. So it's a preliminary progress report on the formalization of IUT, which is joint work in progress with Hoshi, Yamashita, and Yang. So the first topic concerns lean formalization as a communication tool. So since I'm a newcomer to the field, I wasn't aware of how this issue is regarded by experts in the field. But my impression as a novice, as a newcomer, was that the significance of lean formalization is typically regarded as lying in the verification of the logical correctness of a mathematical theory. But in the case of IUT, although this aspect is, of course, quite welcome and of fundamental importance, in fact, the logical structure of the theory is rather simple. And so from the point of view of researchers in IUT, this verification aspect of lean formalization is not a central focal point of interest. Rather, because of the unusual situation that has evolved surrounding IUT, the significance of lean formalization lies in producing a precise record of the logical structure of IUT that is immune to false misinterpretations and hence can be used in a pivotal way to communicate this simplicity in a maximally efficient or precise way to other mathematicians. So I was actually surprised to see that, in fact, this point of view is not an unusual point of view, but appeared in the talks, in many of the talks previously, especially, for instance, explicitly in the first talk today concerning proof engineering, but really in I think many of the talks so far, also the talks from yesterday. So the key to overcoming formidable communication barriers lies in breaking out of the following closely interrelated vicious cycles. So, for instance, I would say, so instantly, can you see the cursor?
Yes.
Yes. Okay. Thank you. So I or someone, a researcher in IUT would say that the logic of supposedly difficult portions of IUT is in fact very simple and elementary. And indeed, it often is just involves very basic logic or set theoretic constructions. And the reaction to this is something like accusations without any mathematical proof. Don't insult me. Mochizuki is only interested in insulting people, or don't insult my intelligence, or it's entirely inconceivable that the ABC inequality could follow from such simple logic. So here I'm reminded of a comment from a remark that was made in Professor Paulson's talk yesterday, that the genius lies in the definitions, and that modulo the definitions, for instance, coming up with a definition of something like a group is what is non-trivial. And in fact, the nature of mathematics is that mathematical proofs are, in fact, relatively simple. So then this would result in a response from my side, but by saying something like, in order to understand the logic of IUT in a genuine, rigorous way, it's necessary to study the original papers in detail, as many others have done. And then this would, the response to this would be something like, it's impossible to become sufficiently motivated to study these papers without confidence that it's correct. For instance, by seeing a sufficiently transparent synopsis of the argument. And then I try to give a simple synopsis, and then we just go back into this loop again. And so in my experience, lean formalization seems to be the first technology that appears to have the technical capacity to allow us to break free of such vicious cycles by providing confidence via a precise and logically verified record of the logical structure of IUT that can be processed by a machine in a fraction of a second in a way that's entirely immune to non-mathematical accusations, such as these accusations, or the human mental fatigue or stress that occurs when trying to comprehend an unfamiliar mathematical theory. So unfortunately, the issue of confidence and correctness has a very human, non-mathematical, social or political dimension. That's to say, no one wants to invest substantial resources of time and effort in a sinking ship. And ultimately, this social or political power can be understood as a reflection of perceived capacity to reliably deliver or ensure long-term mathematical accountability for the mathematical correctness of results or assertions. And again, so lean formalization appears, or more generally, of course, I wasn't I'm not so familiar with other tools such as Isabelle and Hull, but so one can understand this term as I use it in this talk as just referring to this kind of formalization in general. Appears to be the first technology that has the technical capacity to do this in a fashion that is intrinsically independent or unshackled from human social political structures. So one lean expert that I talked to recently talked about how ideally the issue of verification should be a one-to-one dialogue between a human and a machine. It should be completely free from any sort of social or political structures. So from a more technical point of view, at least in my experience so far, the essence of lean formalization, so we're still at the very beginning of this project of formalizing IUT, has consisted of a fundamental reorganization of the theory into suitable, purely formal combinatorial boxes. So this relates to many of the talks, comments made in many of the talks so far about how formalization amounts to a sort of a new way of thinking about writing mathematics or writing mathematical proofs. And so this is also something that I experienced, and it was something that was very refreshing and sort of dramatic. And so I would like to explain in section 4 below some of the technical details of this reorganization in the case of the final portion of the argument of IUT, which has received the most public attention. So this lean code that I will discuss in section 4 below arose precisely from the challenges presented by the task of communicating IUT to mathematicians, arithmetic geometers, who are thoroughly familiar with lean, but who had only a relatively superficial knowledge of IUT. And the situation was remarkable in that it had the effect of faithfully creating in a laboratory these vicious cycles that I referred to on the previous page, but in a generally friendly, productive, non-toxic environment while still preserving the essential dynamics and, unfortunately, overall sense of utter hopelessness and frustration that are characteristic of such vicious cycles. And so the remarkable conclusion is that it's still, of course, a very tiny portion of the whole argument, but in some sense, it's a very key portion of the argument. So my group was able to write skeletal lean code. So it's it's only, so if you delete the comments, it's only about 70 lines. It's not very long. Concerning this final portion of the argument of IUT that sufficiently, successfully and efficiently records in a non-negatable fashion the logic of this final portion of the argument. So on the other hand, it's not ready for public distribution yet because its success as a communication tool depends on the level of understanding of the mathematicians involved on the receiving end of the basic setup of IUT and the main issues involved. So I think that before it's released, there needs to be a lot of work, or a substantial amount of work done to to flesh out this skeletal lean code. So I guess some people refer to this as a snippet of lean code to a degree that it's suitable for release to the general public. So this brings me to an outline of the general strategy for the lean formalization of IUT. So I think of it in terms of these 5 stages. So the first stage is theorem 3.11 of the third paper implies theorem 3.12 because, so this is the top priority because this has received the most public attention. And so we're currently still in the skeletal portion, writing skeletal snippets of lean code for stage 1. And, but in some sense, so stage 1 just shows is, so on the one hand, it's received the most public attention, but in fact, it's not so difficult. And ultimately, when understood properly, it just shows that what one is really interested in is stage 2, which is the proof of 3.11 modulo the first 2 IUT papers. And then, so stage 3 is the first 2 IUT papers modulo earlier results on Abelian geometry for Baignoids and theta functions. Stage 4 is these earlier results. And stage 5 is numerical aspects. So for instance, XBEST is the proof of FLT, Fermat's theorem via IUT. And so this is completely different from the approach, Weil's approach discussed in Kevin Buzzard's talk. So this kind of outline is reminiscent of the situation discussed in Kevin Buzzard's talk. But so this doesn't involve anything to do with automorphic forms or Mazur's theorem or anything like that. And another difference is that it applies to arbitrary number fields, which is very different from the Weil's approach. But so it basically amounts, once you have the theoretical portion of IUT, it basically amounts to a very complicated, but still very elementary computation. So in some sense, one sort of bottleneck for this whole project lies in the fact that my research group only has a very primitive technical capacity, limited primitive technical capacity with regard to writing lean code. So it takes us a great deal of effort even to write small snippets of lean code. And so we're trying to write lean code to sort of pinpoint the main choke points where people are having trouble and to focus on writing snippets for those critical points so that other people who have other research groups who have the capacity to generate large quantities of lean code can finish the job. And so 4 and 5 should be, and to a lesser extent, stage 3 are understood by a larger class of mathematicians and have never also, unlike stage 1, have never been a source of confusion or debate. And so they should be regarded as more long-term goals. So the main goal currently is to concentrate on stage 1 and stage 2. And to hope that other people can get interested in working on these other portions. And again, so especially since stage 5 basically involves very elementary computations, I would think that it might be more suited to auto-formalization. And so, of course, there are currently limits, as has been discussed in earlier talks, to what can be done with auto-formalization. But I think something like stage 5 is the most suited, and stage 4 is the next most suited, and stage 3 is perhaps the next most suited to auto-formalization. So a number of people have, in previous talks in this conference, discussed this point of view that in any lean project, lean formalization project, the most fundamental thing that needs to be done at the beginning is formalization of basic definitions. So this was discussed in, I think, Kevin Buzzard's talk, and also the first talk today by Chelsea Edmonds. And so in the case of IUT, this amounts to formalizing the notion of a functorial algorithm. So in more technical language, this corresponds to the notion of a mutation, which in essence amounts to the theory of species and mutations. So the notion of a functorial algorithm is of fundamental importance, not only in IUT, but also in related Abelian geometry. And in fact, in a broader sense, it appears throughout pure mathematics as a whole. So the main ideas here are the notion of a species, which is a type of mathematical object, such as a group scheme, diagram of schemes, etc., defined in a fashion that is independent of any particular model of ZFC set theory by some set theoretic formula. And a mutation is a construction of one species from another that is defined, again, in a fashion that is independent of any particular ZFC model by some set theoretic formula. So a species determines a category of species objects, while a mutation determines a functor between associated categories of species objects. So species mutations can be thought of as a sort of natural refinement of the classical notions of categories and functors. And so alternatively, and more precisely, if one is willing to go up one step in the hierarchy of universes under consideration, one may regard species mutations as internal categories or functors in the syntactic category associated to ZFC, regarded as a first order theory. So this was pointed out by one lean expert. So in particular, it follows that the lean formalization of species mutations becomes essentially immediate once one has a lean formalization of ZFC as a first order theory. And in the fall of 2025, I discovered that on the one hand, such a lean formalization had in fact already recently been achieved by a young Japanese researcher named Shogo Saito. But on the other hand, I was rather surprised to learn that such a lean formalization does not yet exist in MathLib. And so here we observe that the technical significance of formalizing ZFC as a first order theory lies in the fact that it is necessary in order to be able to work with some indeterminate set theoretic formula phi, as opposed to specific set theoretic formulas like A contained in A and so on, which are natively available in lean. So this was something that I spent a certain amount of time on last fall, but as a result of various consultations with lean experts, I finally reached the conclusion that the formalization of species or mutations in the abstract using some sort of lean formalization of ZFC as a first order theory, although this would ultimately be theoretically desirable at perhaps some later stage in the project, was most likely not necessary for the lean formalization of at least stages 1 to 2 of IUT. That instead one could use standard lean commands for formalizing types of mathematical objects and relationships between various respective component pieces of data in the input-output of a functor. So this seems to be sufficient for formalizing the logic of IUT, at least at the stages, in the case of stages 1 and 2. So this includes the lean code discussed in section 4. So on the other hand, the non-existence of a lean formalization in MathLib of ZFC as a first order theory, even though it seems to be, from what I understand from discussions with various lean experts, to be not particularly technically difficult, the non-existence of this in MathLib made a strong impression on me because especially considering how fundamental ZFC as a first order theory is throughout pure mathematics, it struck me as a remarkable example of the power of lean as a communication tool, namely by faithfully communicating, reflecting the non-existence in the mathematics that has already been formalized in MathLib of the algorithmic construction point of view, which is so fundamental to the logic of IUT as well as related to Nebbian geometry, and which also seems to have been one substantial obstacle to the study of IUT for many mathematicians who are not familiar with this point of view. So some people complain about the way the IUT papers are written. So the way they're written is that they're basically one long algorithm. They're one long complicated construction algorithm. And that's different from what many people would like, namely that the constructions are sort of already known or taken for granted, and one just has lemma, proof, where the lemmas prove various properties about mathematical objects that are already known and taken for granted. But that's not the way the papers work. The papers they're not, all the properties are essentially trivial modulo earlier work. The way the papers are written is that they're written as one long construction algorithm. So before I proceed to section 4, I apologize to the many non-mathematicians in the audience, but I think it's necessary to give a very brief overview of the mathematical content of IUT so I can discuss what it is that we made progress in formalizing. So I think that this discussion can be understood to a substantial extent by people with an undergraduate education in mathematics. So there are various surveys now of IUT as well as various videos on YouTube, but they're not publicly available on YouTube. The URLs for the YouTube videos are available to professional mathematicians upon request. And also various slides for talks are available at these websites. So we start with an integral domain R, such as the ring of integers Z in Q, the field of rational numbers. And we assume that it's equipped with an action of a group G. And we also assume that we're given an integer, positive integer greater than or equal to 2. And for simplicity, we assume that n is non-zero in R. So, and that n has no non-trivial nth roots of unity, which is not an essential assumption. And we write our triangle for the multiplicative monoid given by the complement of 0 in R. So then the nth power map on our triangle determines an isomorphism of multiplicative monoids equipped with group actions given by raising to the nth power. That does not arise from a ring homomorphism. So it's clearly not compatible with addition. So in other words, x plus y the n is definitely not equal to x to the n plus y to the n. So then we consider two distinct copies of this integral domain R and two distinct copies of the group G. We use similar notations for objects with a single dagger and double dagger to the previously introduced notation. And then one may use this isomorphism of multiplicative monoids arising from the nth power map discussed above to glue together these two copies via this nth power map. So here the notion of a gluing may be understood as a quotient set via identifications, but really we want to think of it as an abstract diagram in the style of groups of graphs of groups, or better yet, graphs of ambiguities, which are essentially Galois categories. So we want to glue this ring to one copy of this ring to another copy of this ring along the nth power map. And so this gluing is compatible with the respective actions of G relative to the isomorphism given by just forgetting the labels. But here one has to be careful, and this is fundamental to IUT, and that is that one has to be careful to note the following. So the nth power map is not compatible with addition, as we noted above. And so this isomorphism of groups has to be regarded either as an isomorphism of abstract groups or as an isomorphism of groups equipped with actions on, abstract groups, or as an isomorphism of groups equipped with actions on multiplicative monoids, but not as an isomorphism of Galois groups. So a Galois group is an automorphism group of a ring or a field. So this operation of raising to the nth power is not compatible with addition, so it's not compatible with a ring or field structure. And so we need to think, when we identify these two copies of G, we're identifying them as either as abstract groups or as groups equipped with actions on multiplicative monoids. So the invariant structure with respect to the nth power map, which I refer to as choric, is a weaker structure than the Galois group structure. So this point of view is fundamental to IUT. And formally, you can just think of it as saying that you have to deal with this type, which is an abstract group. You don't have the additional data of the action of the group on some field when you try to regard it as a structure that is common or invariant to both sides, choric to both sides. So the problem of describing certain portions of the ring structure of one copy of R in terms of the ring structure of another copy of R in a fashion that's compatible with the gluing. So it doesn't destroy the gluing. The gluing remains intact, but it's via a single algorithm that may be applied to the common glued data to reconstruct simultaneously certain portions of the ring structures of both these copies of R up to relatively suitable relatively mild indeterminacies. So in other words, what this means is that, for instance, going back to this basic observation that the nth power map is not compatible with addition, we went a way of an algorithm for describing addition in this ring such that it simultaneously gives us x to the n plus y when applied to x and y. It simultaneously gives us xn plus y, x to the n plus y to the n, and the quantity x plus y to the power n. Perhaps up to relatively mild indeterminacies. So at first, this problem seems hopelessly intractable. So here we want to note that considering portions of this diagram is important, because later we want to decompose this diagram into pieces so that we can consider symmetry properties. So So here the main observation is that raising to the nth power is not symmetric with respect to the input and output. So so another way to put it is raising to the nth power is not the same as taking the nth root. It's very different. It's not symmetric, but we would like to consider structures that are symmetric with respect to the input and output of the nth power. So one well-known, so this is more advanced than undergraduate mathematics, but when n is equal to p, working modulo p, the theory of crystals gives us a way to consider structures that are common to both sides, despite the fact that so R is not of characteristic P, but modulo P, we obtain a ring homomorphism, and so one can consider one can use the theory of crystals to obtain structures that are common to both sides. So another important example in this context is Folting's proof of the invariance of the height of elliptic curves under isogeny under the assumption of the existence of a global multiplicative subspace. So this is a special case of Folting's proof of the Tate conjecture. And so this is discussed in more detail here for people who are interested. So the point of IUT is to construct what's called the multiradial representation for the theta pilot, which may be thought of as a realization of this kind of algorithm. So it's an algorithm that takes as input data only the structures that are common to both sides, the multiplicative monoid and abstract group structures. And it constructs a multiradial representation for the theta pilot. So one can think of the theta pilot as the nth power, the image of the nth power map. So a common container that contains both sides, both ring structures simultaneously, up to certain indeterminacies, to certain distortions, which are relatively mild. So the point of doing this, and so this is very similar to it's a sort of non-scheme theoretic version, or I can think of it as an abstract and abelian version, because the key to constructing this multi-radial representation lies in making use of n-abelian geometry, which is a field of mathematics that allows you, roughly speaking, in certain cases, to reconstruct the ring structure from these abstract groups that are common to both sides. So one also uses theta functions and Kummer theory to relate these Frobenius-like versions, which are the abstract monoids, to état-like versions, which are the versions reconstructed via n-abelian geometry from G, from the Galois group. So one can think of this as a sort of n-abelian or non-scheme theoretic version of the scheme theoretic argument given in Folting's proof. And the idea here is that the point of considering the nth power map and obtaining a situation where it looks like the nth power map is a ring homomorphism up to a relatively small distortion, is that one is interested in bounding the height of an elliptic curve. So this, roughly speaking, corresponds to the log of the absolute value of the the coefficients defining the equation of the elliptic curve. And so raising to the nth power multiplies the height by n. On the other hand, so raising to the nth power corresponds to the n comes out here, and raising multiplying by n, and saying that this is roughly unchanged up to a relatively mild error term means that the height is bounded. So in IUT, the multiradial representation is obtained by means of a sort of analytic continuation along a certain portion, which I refer to as the infinite h of the log theta lattice. So one considers this log theta lattice and this infinite h portion. And so each bullet in the log theta lattice corresponds to a certain kind of model of ring theory, or the standard ring theory or scheme theory surrounding an elliptic curve. The theta link, each theta link, corresponds to the nth power map discussed above. And the log link locally at non-Archimedean valuations looks like the p-adic logarithm between distinct ring structures. And the idea is that one wants to consider various descent operations that revolve around the establishment of certain choricity or symmetry properties. So recall that the group actions are choric, they're common to both sides for this nth power map type operation. And so we want to use that as that relatively weak data to transport the ring structure on this side to the ring structure on this side, to describe the ring structure in terms that make sense simultaneously for this side and for this side. And the way one does this in IUT is not by doing this directly, but rather by descending. So what this means is that when introduces what one might call fuzzifications corresponding to the introduction of various kinds of indeterminacies, relatively mild indeterminacies, that allow one to construct invariants with respect to the log link. And remember that the log link has the effect of juggling, the logarithm has the effect of juggling addition and multiplication. And here, the nth power map basically, if you think in terms of a local field, the nth power map basically, or the log that we discussed here, the nth power map dilates the height, it dilates the valuation group portions of the ring. And there's a non-dilated portion, which consists of the local units, for instance. And so the idea is that one wants to construct invariants with respect to the log link, and that by doing so, one obtains a construction that is symmetric with respect to the two sides of the theta link, which is quite amazing because, as I said, raising to the nth power is not symmetric with respect to input and output. So one uses Abelian geometry and theta functions and so on to construct invariants with respect to this log link in such a way that one obtains a construction of the ring structures up to relatively mild indeterminacies that is symmetric with respect to both sides. So one can think of this as a sort of rotation of the theta link, which is mysterious in that, so it's raising to the nth power. So you don't know how the heights or these correspond to what are called log volumes. So the theta link corresponds to multiplying log volumes by n, whereas the log link preserves the logarithm preserves log volumes, and so one can think of the multiradial representation as a sort of way of rotating, of obtaining a sort of miraculous rotation of this log volume dilating theta link into the log volume preserving theta link. So this is a brief summary of IUT. And so the significance of the multiradial representation lies in the fact that, so as I explained on the previous page, by means of the technique of descent, so descent basically means that it's supposed to be reminiscent of the way the term is used in classical growth and style scheme theory, but it's not exactly the same. It's sort of an abstract version of that kind of descent, and that is that one wants to. So a priori, the ring structures are a very strong kind of a structure. But one wants to construct the objects that one is interested in, not from the very strong and delicate structure of a ring, but from a priori weaker structures, which are often group theoretic, typically group theoretic. So so one wants to construct the theta pilot, which one can think of as the image of the nth power map. The theta pilot in the domain of the theta link. So the theta pilot here. In terms of purely group theoretic data, which is referred to as the Étal-Hodge theater, that is vertically choric, which means that it's invariant with respect to the log link. So the p-adic logarithm, so locally at non-Archimedean violations, the log link looks like the p-adic logarithm. So the p-adic logarithm is very far from being a ring isomorphism, but it induces, or it's compatible with, an isomorphism of certain arithmetic fundamental groups, which one can think of as just an enhanced version of the notion of a Galois group. And so the Galois groups map isomorphically to one another via the log link, just as in the case of the theta link. Here we consider Galois groups that are larger than the Galois groups that occur in the theta link. So in the nth power map, we have this G that is choric, if you think of it as an abstract group. In the case of the log link, we have larger groups that surject onto the Galois groups that appear, larger Galois groups that surject onto the Galois groups that appear in the theta link. So one can think of it as being this kind of situation. So the theta link involves a gluing, which recently has been referred to by some people as a BPS, or basic prime strip. So this is basically shorthand terminology for the original terminology of the IUT papers, which is this terminology. Since this notation is rather difficult to read, so people refer to this as a BPS. So this is the G that corresponds to the G that occurs in the nth power map. This is the gluing data in the nth power map. And these are the larger Galois groups that surject onto this G. And so this G one only knows up to isomorphism. But the point is that if one works with, one has this group G that one only knows up to isomorphism, and then these surjections of, so this group is isomorphic to this group, but it's on the other side of the nth power map. But the point is that one has the same up to isomorphism surjection here and here. And so these two, if one works with this group theoretic, Galois theoretic data, so even though I say Galois groups, they're groups, abstract groups that arise as Galois groups, we have to think of them, it's important to think of them as abstract groups, not as Galois groups. This data is symmetric, unlike the nth power map. So again, the nth power map, raising to the nth power is not the same as taking the nth root. So it's not symmetric with respect to input and output. But what is amazing is that if you look at these Galois groups as abstract groups, then one gets a diagram that is symmetric with respect to the input and output of this nth power map. So notice the theta link. So this is sort of the fundamental or one of the fundamental technical observations underlying IUT. And so incidentally, I should say with regard to NMB and geometry that some people who have had problems understanding IUT have taken the point of view that that Nabelian geometry, the Nabelian geometry used in IUT is unnecessary. And the argument that they give is that since Nabelian geometry is used to reconstruct ring structures from abstract Galois groups, once one has the ring structures, one can forget about the Galois groups. And so there's no need to use Nabelian geometry if one just works with rings. And that's a fundamental misunderstanding of the situation, because the reconstruction algorithms of Nabelian geometry are functorial with respect to isomorphisms of groups and rings, but they're not functorial. They do not satisfy any functoriality properties with respect to raising to the nth power. So this is very fundamental. One wants to use Nabelian geometry because Nabelian geometry allows you to access the ring structure data from the purely group structure data. And the group structure data, again, it has this advantage that the ring structure data does not satisfy the ring structure data. The ring structure is not symmetric with respect to the nth power map, the input and output of the nth power map. Whereas these abstract group structures are symmetric. This is what is fundamental to IUT. So the theory surrounding this operation of descent is summarized in the first two commuting triangles of the following diagram of species and mutations. So one can think of it as just certain types of data and certain algorithms that input some kind of data, some type of data, and output some other kind of data. And so the multi-radial algorithm can be thought of as an algorithm that inputs a BPS, this glued data in the nth power map, which corresponds to the theta link, inputs a certain kind of data and outputs this multi-radial representation, which I discussed in the previous section. So the first, this first triangle, commuting triangle, expresses the multi-radial algorithm as an algorithm that, so this BPS is glued to the zero column, so that means the this column. So this column I refer to as the zero column, and this column I refer to as the one column. So it's the x coordinate. So the first triangle expresses the this multi-radial algorithm as an algorithm that constructs the theta pilot. So this is the image of the nth power map in terms of this zero column ring structure. So that's sort of the a priori way that this is constructed. And then the second commuting triangle, which involves this descent arrow, expresses this multi-radial representation as so descent means that this construction from a priori relatively strong data, in fact, can be obtained as a construction that factors through relatively weaker data. And this is done precisely by considering suitable indeterminacies, which are called in 1, 2, and 3. And so, in other words, the zero column has various ring structures at each of these bullets. And as I said, this étal Hodge theater in the zero column. So this is the étal Hodge theater in the zero column, and this is the étal Hodge theater in the 1 column. This is vertically choric, which means that it's invariant. It's data that's unlike the ring structure, which is not preserved by the p-adic logarithm. These group structures are mapped isomorphically. So when considered up to isomorphism, they're invariant vertically. And so it's weaker data. But what this is saying is that the multi-radial representation can be, descent allows you to introduce relatively mild indeterminacies that allow you to reconstruct this data from weaker data. And then the third triangle just expresses this composite. So relatively elementary operations that can be applied to the multi-radial representation that, roughly speaking, amount to taking the determinant of the module over a ring generated by a certain topological module that appears in the multi-radial representation. So they're relatively elementary operations. So that's the second triangle. And so then the fourth triangle, which is the topic, the subject of this snippet of lean code that I have not made public, but I want to discuss in this talk, is so the point here is that the main conclusion that one wants to obtain in IUT is that one wants to be able to compare the nth power with the original non-nth power in the same copy of ring theory. So what this descent data is, what this descent operation is telling you is that although the theta pilot, so the image of the nth power map, a priori it's in the zero column, so it's on this side, on the left-hand side. It can be expressed up to suitable indeterminacies in terms of this étal Hodge theater, which is essentially group theoretic, and which has this fundamental symmetry property, which means you can't tell whether this étal Hodge theater came from the zero column or from the 1 column. And once you know that, you can apply this to the data that arises from what's called the Q pilot. So this is before one takes the nth power, and the étal Hodge theater in the 1 column. And so it's this fourth triangle that allows one to make the comparison between the Q pilot and the theta pilot in the same ring theory, because the ring theory can be thought of as being reconstructed from this étal Hodge theater up to certain indeterminacies. And so because now we're reconstructing it from the same étal Hodge theater, this they can be compared in the same container. So this is what the fourth triangle is about. So the skeletal lean code, the snippet of lean code, roughly 70 lines, basically encodes this from a sort of data processing point of view. And so this is the portion of the argument that, as I said, allows a simultaneous comparison relative to a single ring structure, a common container of the image of the nth power map, which is the theta pilot, and domain of the theta pilot of the nth power, which is the Q pilot. And so this is the portion that has received the most public attention and has been so it's the final portion of 3.11 implies 312. And so this is why we chose to concentrate on this aspect first. And so this has been effective in I'm sorry, is someone saying something? Okay. So this has been effective in communicating this very final portion in a situation where natural language communications were not effective. And so this is what was remarkable. And so in section 2, I referred to a reorganization or decomposition of the way the argument was written in the original paper. So this diagram on the previous page, in some sense, reflects this reorganization. So this final portion of the argument of 3.11 implies 3.12, I refer to as 3.11.5 implies 3.12. So one can think of 3.11.5 as somewhere between 3.11 and 3.12, but perhaps a better way to think of it is as shorthand for 3.11 plus a certain remark, rather long remark, 3.9.5, that appears in the third IUT paper. So 3.11.5 never appears in the IUT papers, but so in some sense, a certain portion of 3.12 was, so this reorganization was obtained by moving a certain portion of 3.12 to 3.11.5. So this is a portion that relates to this remark 3.9.5. And this allows one to concentrate on the simultaneous comparison aspect. And so what that means is that it decomposes this simultaneous comparison into basically this portion and this portion. So this portion it doesn't involve much of the theory. It's relatively simple. Whereas this portion involves most of the theory. This is the image of the nth power map, the theta pilot. And this portion involves, so this whole portion of the diagram. So so the next step is to write skeletal lean code for this portion. So for the second and third commuting triangles, which so the first, so this fourth triangle involves what I refer to as the SHE property, which stands for simultaneous holomorphic expressibility, whereas this portion involves what I refer to as APT, or algorithmic parallel transport, which concerns the way in which one expresses gluings up to indeterminacies. And so this is a relatively simple set theoretic kind of issue, but it seems to have been confusing for some people. And so we're currently writing a skeletal lean code for this portion. And so, in fact, both portions also involve another fundamental property, which I refer to as IPL, or input prime strip link. The input prime strip link property, which refers to the relationship between the data contained in the input BPS of the multi-radio algorithm and the data contained in the output of the algorithm. So IPL, in fact, occurs in both portions. But so anyway, so this talk was to report on this portion and we're currently working on this portion. So this is where the project stands at the present time. Okay, thank you for listening.
Thank you very much. Thank you. We've got a couple of questions coming in, and do keep bringing them forward. So one question, given the current state of lean, do you think that it's in principle possible to prove the ABC conjecture as it can be formulated currently in lean? So here, using the existing definitions rather than alternative definitions.
The theory of IUT involves numerous definitions. So certainly mathlib is not sufficient. As I explained in section 2 with all these stages, there's a lot of work that needs to be done. And so this involves many definitions of new types of mathematical objects. But what I will say is that I am 100% convinced that there's no so this also relates to what was discussed in Kevin Buzzard's talk, that there's no theoretical obstruction to doing all of this in lean. It's just going to be a lot of work. And that's why I'm concentrating on stages 1 and 2. We're still at stage 1, and the idea is to concentrate on the portions that have received the most public attention, that people find most difficult to understand, and writing snippets of lean code for those portions. And those portions involve very large black boxes. And in particular, those black boxes contain many definitions that have not been formalized. But I think it's just a matter of time and effort. There are no sort of obstacles in principle.
Sure. Yeah, I think the thrust of the question was the ABC conjecture can be formalized with existing theorems, existing definitions in MathLib. And the proof might involve new definitions. I think which you've indicated.
Yes.
But the existing definition in terms of stating the conjecture should be sufficient, even if you have to develop new tools and new definitions to prove it.
Right. So of course, stating the ABC inequality is a very elementary issue. So there's absolutely no problem there. Mm-hmm. Right. But yes. Yeah.
Okay. Thank you. Another question. It seems that the key question for this is the fourth triangle, and so there's just a query as to why not focus on the fourth triangle, or do you need the second and third as a necessary prerequisite to be able to discuss the fourth one properly in lean?
Well, so the current the lean snippet that I talked about in the talk concerns the fourth triangle, and so by formulating black boxes, sufficient suitable black boxes, you can talk about the fourth triangle. You can formalize the fourth triangle without talking about the second and third triangles. There seems to.
Yeah. So sorry. Yeah. Another person keeps unmuting accidentally, I think. Thank you. Yeah, I think we caught that. So you mentioned lean doesn't have a formalization of ZFC as a first order logic. Can you expand on that and why it's important for IUT? And I wonder whether also you might just comment on why the choice of lean, if that's the case as well.
Well, so I was told by a lean expert. I'm not an expert on the content of MathLib, but I was told that it doesn't currently exist in MathLib. But on the other hand, it's something that's not particularly difficult, and so it's not that it doesn't exist in MathLib because it's terribly difficult to do, but because it just doesn't. People haven't been sufficiently interested in doing it, at least for MathLib. And so the reason that it is relevant for IUT is because one needs to talk about types of mathematical objects and algorithms that construct one kind of mathematical object from another. And so from the point of view of usual mathematics, the only way to define these kinds of notions is by using set theoretic formulas. And that's where ZFC as a first order theory comes in. But from the point of view of lean, and of course, I'm very far from being an expert on the structure of lean, but the point is that by using types and various other sort of standard features of lean, one can, in some sense, express the logic that that is used when one considers species and mutations, without actually explicitly talking about set theoretic formulas. Although as I said, I think that it's theoretically desirable that at some point someone does this in terms of the set theoretic formulas, which was the original mathematics, the original way it was written in the papers. But from the point of view of expressing the logic of arguments involving species and mutations, one can, in fact, at least as far as I can see, use standard lean commands to express this logic. Yeah.
Okay, thank you. And a final question before we have a short break. How long do you expect stage one to take? Is it the order of months, years? Do you have a feeling for that?
Well, so as I said, the main bottleneck is that my research group consists of mathematicians who are not who have a very minimal knowledge of lean, and so we don't have the ability to generate large quantities of lean code. And so, given sort of an ideal collection of workers, I wouldn't think that stage one should take more than a year, maybe not even more than half a year. But the problem is sort of organizing people and communicating with people, and it's that kind of social organizational issue. And so it's difficult for me to tell, as a matter of fact, how long it will take. But in an ideal world, it shouldn't take more than a half a year to a year. I wouldn't expect that.
Thank you. And then I guess this is where there is important possibilities of auto-formalization, but also cross-community collaborations to be able to do some of this and bring different expertise from different areas. Let's thank our speaker again.